What causes the immense cosmic expanse to gather into stable structures, as if following an invisible algorithm? This question has become one of the central pillars of modern cosmology, because any explanation of how the universe is built rests upon understanding why enormous amounts of matter choose certain forms rather than others. Early models once assumed that matter was spread evenly, yet later observations revealed something far more intricate, a complex, hierarchical system stretching from small clusters of stars to colossal, plateau-like superclusters of galaxies. At the foundation of this architecture lies the interaction between matter and the geometry of space and time itself, where motion and evolution are shaped by tiny density fluctuations that arose an unimaginably brief moment after the initial cosmic expansion. One of the key ideas is that these primordial irregularities were amplified by a process known as cosmic inflation. Inflationary theory proposes that, in the earliest fraction of a second, space expanded at an extraordinary rate. This helps explain why the region we observe today has nearly the same temperature everywhere, even though distant areas had no time to exchange energy. In this picture, microscopic quantum fluctuations, stretched to astronomical scales, became the seeds of future galaxies. Especially important is the role of fields that may have governed phase transitions within the energy landscape of the young universe. Many researchers now believe that large-scale structure is not random, but reflects fundamental properties of cosmic space. Observations suggest a vast network resembling a web of filaments and voids, where galaxies align along dense strands, while enormous empty regions form bubble-like cells. Each supercluster can span billions of light years. The filaments connecting them create what scientists call the cosmic web. Theoretical models describe this web as emerging primarily from the influence of dark matter. Dark matter acts as an invisible framework upon which ordinary baryonic matter gathers to form galaxies and clusters. It cannot be detected directly, yet its presence is revealed through gravitational effects. One leading hypothesis suggests that dark matter consists of particles that interact extremely weakly and do not participate in electromagnetic processes, which explains their invisibility. Other models imagine more complex possibilities, such as dark atoms, dark chemistry, and even entire dark galaxies. These ideas remain speculative, but they hint that the visible universe may be only a small fraction of a far larger hidden structure. Dark energy represents a very different component. It appears to drive the accelerated expansion of the universe. Observed through distant supernova and subtle patterns in the cosmic microwave background, some theories interpret dark energy as a property of empty space itself. Others suggest a dynamic field whose strength changes over time. There are even proposals that accelerated expansion arises from modifications in the geometry of spacetime, rather than from a separate energy source. These possibilities shape our understanding of the universe's ultimate fate. To understand structure formation, scientists also study why galaxies form groups and why those groups merge into larger systems. One hypothesis suggests that the universe may exhibit partial fractal behavior on certain scales. This means similar patterns might repeat from stars within galaxies to galaxies within superclusters. While perfect fractality breaks down on the largest scales, these models remain valuable for exploring how matter self-organizes under gravity. Gas cooling plays a crucial role in cosmic evolution. When temperatures fall below specific thresholds, dense clumps form within clouds. These clumps eventually ignite as stars. The first generation of stars consisted almost entirely of hydrogen and helium. They were enormous, brilliant, and short-lived. When they died, they enriched space with heavier elements. This enrichment made possible rocky planets, complex chemistry, and stable planetary systems. Chemical elements thus become cosmic tracers, allowing scientists to follow the movement of matter across billions of years. The cosmic microwave background is one of the most powerful windows into the early universe. It preserves a faint imprint of conditions shortly after the cosmos cooled from its hot, dense state. Tiny temperature variations in this radiation correspond to the earliest density fluctuations. These microscopic differences became the seeds of all later structures. By analyzing them, scientists refine cosmological parameters, the proportions of ordinary matter, and dark energy. This allows increasingly precise simulations of how today's cosmic architecture emerged. Another fascinating idea is that our universe may be part of a larger multiverse. In this view, many universes could exist, each with its own physical constants and laws. Our universe might simply be one where conditions permit long-lived stars, stable atoms, and complex structures. Though purely theoretical, this concept pushes physicists to seek deeper unifying principles between quantum mechanics and cosmology. Related to this are theories of hidden dimensions. String theory, for example, describes fundamental particles as tiny vibrating strings. Such vibrations require additional spatial dimensions beyond the familiar three. These extra dimensions may be compact and tightly curled, far too small to observe directly. Yet their geometry could subtly influence how gravity behaves and how matter organizes on large scales. Gravitational waves have become a new tool for exploring cosmic structure. These ripples in space-time are produced by the motion of massive objects. In theory, waves generated in the earliest moments of the universe could carry information about phase transitions and high-energy fields from the dawn of time. Listening to these ancient echoes allows us to glimpse epochs far beyond the reach of light. If traces of such primordial gravitational waves can one day be detected, they would illuminate processes that occurred long before atoms themselves existed. For now, our instruments are limited by sensitivity. Yet future observatories may bring us closer to a moment when this ancient information becomes accessible. Some cosmological models suggest the presence of large-scale anisotropies, subtle directional preferences, imprinted by the universe's initial conditions. This would mean that matter distribution might possess a preferred axis or orientation. Hints of such deviations arise from detailed studies of the cosmic microwave background, where certain analyses reveal faint departures from perfect uniformity. There are hypotheses that these irregularities could result from motion through an enormous structure, or from interactions with regions beyond the observable cosmos. These ideas remain highly debated because they challenge foundational assumptions about isotropy and homogeneity. Understanding today's universe also depends on precise measurements of the expansion rate. Different methods, however, produce slightly different values. This puzzle is known as the Hubble tension. One possibility is that local variations in matter distribution influence measurements. Other hypotheses propose new physical processes that alter expansion dynamics at different cosmic epochs. Solving this mystery could require revising the entire cosmological model, since the expansion rate determines the universe's age, density, and long-term destiny. A study of structure extends beyond what we can observe directly. Because light travels at a finite speed, regions whose signals have not yet reached us remain hidden. Yet theoretical models allow scientists to extrapolate what such regions might be like. Some scenarios propose an infinite cosmos containing countless structures similar to those we observe. Others suggest a finite universe with a complex topology, space that curves back on itself. In such a cosmos, a beam of light could, in principle, return to its point of origin after an unimaginably long journey. These geometries require deep mathematics and remain unconfirmed. What determines a galaxy's evolutionary path? Why can systems containing billions of stars maintain coherent forms for billions of years? Modern astronomy treats galaxies as dynamic systems, constantly exchanging energy and matter with their surroundings. Their appearance may seem stable, yet internally they are always changing. In the early universe, the first clumps of matter began merging under gravity. These clumps became the seeds of galaxies. At that time, heavy elements were scarce. Gas cooled more slowly. Star formation occurred under extreme densities. Many early stars were enormous and short-lived, ending their lives in powerful explosions. Their remnants enriched space with heavier elements, laying the groundwork for future generations of stars and planets. Galactic structure depends not only on mass, but also on angular momentum. Small primordial irregularities could transfer momentum to forming clumps, causing them to rotate. As clouds collapsed, this rotation intensified. The result: disk-shaped galaxies. Yet not all galaxies possess disks. Elliptical galaxies, oval in shape, contain stars moving in random directions. Such systems likely formed through violent mergers. Collisions play a central role in galactic evolution. Simulations show that interactions between large galaxies dramatically alter stellar motions. Gas clouds compress. New starbursts ignite. If two galaxies of similar mass collide, the result is often an elliptical galaxy. If a large galaxy absorbs a much smaller one, the disk may survive, though disturbed. These processes are observed today. Spiral galaxies gradually consuming small satellites. Dark matter appears essential to galactic stability. It forms a massive halo surrounding visible matter. This halo deepens the gravitational well, preventing outer stars from flying apart. Observed stellar velocities do not match predictions based only on visible matter. This discrepancy is one of the strongest evidences for dark matter's existence. Inside galaxies, stars, gas, and dust interact continuously. Stars form, live, returning material to space. Gas flows under gravity and radiation pressure. In many models, gas drifts toward the galactic center, feeding a supermassive black hole. This triggers active galactic nuclei. Powerful jets of energy can extend millions of light years. Such activity can suppress star formation by heating surrounding gas. A form of cosmic self-regulation may exist, where black hole activity controls the growth of stars and stabilizes the galaxy. Elliptical galaxies often contain mostly old stars and little new star formation. Spiral galaxies, by contrast, display graceful arms. These arms are not rigid structures. They are density waves. Stars move in and out of them, like cars passing through slow-moving traffic. This explains their long-term persistence. Interactions with neighboring galaxies can amplify spiral patterns, creating sweeping arms that stretch far beyond the main disk. In some galaxies, astronomers observe bar-shaped structures, elongated regions stretching straight through the center. Models suggest that these bars arise from instabilities within the galactic disk. They redistribute energy and angular momentum, gradually reshaping spiral arms. Bars also play a crucial role in channeling gas toward the central regions, which can enhance the activity of the galactic nucleus. Over billions of years, such structures may form, dissolve, and reappear, revealing galaxies as truly dynamic systems. Particular attention is given to dwarf galaxies. Despite their small size, they play an outsized role in cosmic evolution. Large galaxies are believed to have grown by absorbing countless dwarf systems. Dwarf galaxies display remarkable diversity. Some contain extremely old stars. Others show intense ongoing star formation. Because many dwarfs preserve primitive characteristics, they offer glimpses into conditions of the early universe. When they interact with larger galaxies, they produce stellar streams, long ribbons of stars stretching across space, now detected by modern telescopes. The intergalactic medium also shapes galactic destiny. Between galaxies exists a thin gas capable of slowing moving galaxies. This effect is called dynamical friction. Over time, galaxies lose orbital energy and drift closer together. Within clusters, such interactions occur frequently, accelerating mergers. Hot gas and clusters can also strip galaxies of their internal gas, depriving them of material for future star formation. Some models treat galaxies as open systems, constantly accreting matter from their surroundings. This inflow may have been especially important in the early universe, when gas was abundant. Even today, observations suggest that galaxies continue to acquire fresh gas, renewing their disks and sustaining activity. Chemical composition provides another window into galactic history. Inner regions tend to contain more heavy elements, indicating many generations of stars. Outer regions contain fewer heavy elements, signaling slower star formation. These gradients help reconstruct a galaxy's evolutionary timeline. An intriguing line of research focuses on galaxies that appear to contain little or no dark matter. In some objects, stellar motions can be explained without invoking extra mass. This challenges conventional models. One hypothesis suggests such galaxies formed after collisions that stripped away most of their dark matter halos. Another proposes modified laws of gravity at extremely low accelerations. These ideas remain controversial, but stimulate ongoing debate. What determines a star's stability? Why can nuclear reactions shine steadily for billions of years? Stars achieve conditions unmatched anywhere else. They serve as natural laboratories for extreme physics. Stars are born within cold molecular clouds. As gas collapses, temperature rises. Eventually, hydrogen begins fusing into helium. This fusion releases enormous energy. Outward pressure balances gravity. A state called hydrostatic equilibrium is achieved. This balance defines a stable star. Low-mass stars burn fuel slowly. Their lifetimes exceed the current age of the universe. These stars are known as red dwarfs. They shine gently, rarely erupting, and may persist for trillions of years. They are likely the most common stars in existence. Massive stars evolve differently. Their cores reach temperatures allowing fusion of heavier elements: carbon, oxygen, neon, magnesium, silicon, and finally iron. Iron marks the end. Fusion beyond iron consumes energy. The star becomes unstable. The core collapses. Outer layers are expelled in a colossal explosion. During collapse, electrons combine with protons, forming neutrons. A flood of neutrinos carries away energy. These elusive particles may help drive the explosion itself. The precise mechanism remains under study. The collapse leaves behind either a neutron star or a black hole. Neutron stars pack more mass than the Sun into a sphere only tens of kilometers wide. Their interiors may contain exotic forms of matter, quark matter, hyperons, or other unknown states. Because such conditions cannot be recreated on Earth, neutron stars offer a rare window into fundamental physics. Black holes represent some of the most extreme objects in existence. They form when matter collapses so completely that gravity becomes impossible to escape. Their inner structure is hidden behind the event horizon. Although we cannot observe what happens inside, mathematical models describe how they behave from the outside. Space around a black hole curves so intensely that even light cannot escape. By studying accretion disks around supermassive black holes in galactic centers, scientists gain insight into physics near the horizon. Temperatures reach extraordinary levels. Matter moves at relativistic speeds. These conditions allow us to observe the bending of space and time itself. Another area of research focuses on stars with unusual characteristics. Some objects shine more brightly than their mass would suggest. Many of these are binary systems, where two stars orbit closely and exchange material. If one star is a white dwarf, accreting matter from its companion can trigger a thermonuclear outburst called a nova. In more extreme cases, the entire star detonates in a Type Ia supernova. These explosions serve as cosmic distance markers, helping map the large-scale structure of the universe. There are hypotheses about stars, so massive that their internal structure is governed not only by radiation pressure, but by higher-order instabilities. Such stars may have existed in the earliest cosmic epochs. The first generations of stars could have been far more massive than those we observe today. Their deaths may have created the first black holes, which later grew into the supermassive giants found in galactic cores. Stellar winds are another key element of stellar evolution. They are streams of material flowing from a star's surface. In massive stars, winds can be extremely powerful, removing large amounts of mass over time. This mass loss influences how a star ultimately ends its life. In lower mass stars, winds are gentler, yet they still shape the surrounding medium and can trigger new star formation. Pulsating stars exhibit periodic changes in brightness. These variations arise from physical processes in their outer layers. In some models, helium ionization traps energy, causing expansion. Cooling follows, then contraction. These repeating cycles allow such stars to function as standard candles, crucial for measuring cosmic distances. Rapidly rotating stars form another fascinating class. Their spin can be so fast that centrifugal force flattens them. Rotation may enhance internal mixing, altering core composition and extending or shortening lifetimes. These effects remain an active area of study. Some speculative models propose objects that do not fit traditional categories. Certain hypothetical stars may contain large amounts of dark matter. If dark matter particles annihilate, such stars could gain energy from this process rather than fusion alone. These ideas remain theoretical, but they broaden our understanding of what stellar objects might be. Magnetic activity plays a major role in stellar behavior. Powerful flares arise from twisted magnetic fields. These eruptions eject plasma into space. In small stars, such flares can be even stronger than those seen on sun-like stars. Magnetic activity affects nearby planets, shaping their atmospheres and influencing habitability. Star clusters offer natural laboratories for studying stellar evolution. All stars within a cluster formed around the same time. This allows astronomers to isolate the role of mass in evolution. Globular clusters are especially important, as many contain extremely ancient stars. Some may have formed before galactic disks themselves. There are also hypotheses about exotic compact objects denser than neutron stars. They may contain strange matter or unfamiliar states of particles. Though unconfirmed, they stretch the limits of theoretical physics. Another idea suggests that some black holes form through direct collapse without a visible supernova. This process could produce intermediate mass black holes. Such mechanisms may help explain how supermassive black holes formed so early in cosmic history. Planetary systems raise another profound question. What allows a system to remain stable for billions of years? Thousands of exoplanets have now been discovered. Their diversity reveals that planetary formation is extraordinarily versatile. Protoplanetary disks arise from gas and dust left after star formation. Inside these disks, particles collide and stick together. Small grains become pebbles. Pebbles become planetesimals. Planetesimals collide, forming ever larger bodies. Through this quiet, persistent growth, entire worlds are born. The pace of planetary formation depends on the density of material and the complex motions within the disk. Several models attempt to describe how planets are born. One of the central ideas is the accretion model, where tiny particles slowly gather, merge, and grow into larger bodies. Another hypothesis suggests that massive gas giants may form extremely quickly through gravitational instability, when dense regions of the disk collapse directly. These different possibilities raise a profound question. How universal are the conditions inside protoplanetary disks? If a disk is dense, giant planets may appear rapidly. If the disk is sparse, growth proceeds slowly and may produce only small rocky worlds. A planet's position within a system is shaped not only by where it forms, but also by migration. Migration helps explain the existence of hot Jupiters, gas giants orbiting very close to their stars. Traditional models once assumed giant planets could form only far away, where cold temperatures allow gas to condense. Today, scientists believe many giants form in distant regions and later drift inward. Migration can be driven by interactions with disk gas, gravitational resonances, and encounters with other bodies. Rocky inner planets follow a different evolutionary path than gas giants. Near a star, temperatures are high. Frequent collisions melt material. Magma oceans may form. Heavy elements sink toward the core. Lighter materials rise to create the mantle. If the core remains molten and mobile, a magnetic field can emerge. Such a field acts as a shield, protecting the atmosphere from stellar winds. Outer regions of planetary systems receive far less energy. Here, icy bodies dominate. Ice giants may form, composed of water ice, ammonia, methane, and other compounds. At low temperatures, unusual chemical reactions become possible. Methane snowfields, clathrate structures, exotic ices that persist for eons. Orbital stability remains a central issue. Planets constantly influence one another through gravity. Orbits may change in tilt, shape, and period. In crowded systems, chaotic behavior can arise. Yet many systems remain stable for billions of years. Resonances play a key role. When orbital periods form simple ratios, gravitational interactions may either stabilize the system or amplify disturbances. The discovery of exoplanets has transformed our understanding of possible planetary environments. Some worlds are hot enough to melt metals. Others orbit so close to their stars that their atmospheres evaporate. Some gas giants trail vast comet-like tails. Certain planets complete an orbit in just a few Earth days. Others follow tilted or highly inclined paths, hinting at turbulent early histories. There are hypotheses about ocean worlds, planets covered by deep global seas. On such worlds, pressure at the ocean floor may create exotic forms of ice. Internal heating from radioactive elements could drive circulation. Complex chemistry might emerge. Some models propose carbon-rich planets. These worlds could possess diamond-like mantles, graphite-covered surfaces, and hydrocarbon seas. They may form in systems with high carbon-to-oxygen ratios. Water could be rare or absent. Chemistry would follow unfamiliar pathways-tidly locked planets present another possibility. One side always faces the star. The other remains in eternal night. Dayside surfaces may host magma oceans. Nightside regions could be frozen. Atmospheric currents may transport heat, creating powerful winds and dramatic weather systems. Particularly intriguing are rogue planets, worlds that wander through space alone. Ejected from their original systems, they may still retain internal heat. Some may hide subsurface oceans beneath thick ice shells. Such environments could support long-lived chemical processes, even without starlight. The study of exoplanet atmospheres reveals chemical composition, temperature, pressure, and cloud layers. Spectroscopy can detect water vapor, methane, carbon dioxide, and more. Some atmospheres are stable. Others gradually escape into space. Close-in planets may lose their gas envelopes, leaving behind rocky cores. Many super-Earths and mini-Neptunes may be remnants of once larger giants. Magnetic fields also matter. They can shield atmospheres and shape climate. Without magnetic protection, stellar winds may erode atmospheric layers. As observational techniques advance, astronomers explore increasingly exotic possibilities. Among them, planets orbiting binary stars, moving through skies lit by two suns. These systems possess complex dynamics because gravity is shared between two stellar sources. Yet observations show that such worlds can remain stable. In other cases, a planet may orbit one star while still being strongly influenced by a second, creating intricate orbital patterns. Why are the small bodies of a planetary system so important for understanding the universe, even though their mass is tiny compared to planets and stars? Because they preserve memory. They are time capsules. Small bodies retain their original chemical and structural composition. They allow scientists to reconstruct the conditions present during the earliest stages of planetary formation. They display complex behaviors, gravitational interactions with planets, thermal evolution, unusual rotational states. A special place belongs to moons. Their origins are diverse. Some formed alongside their planet inside an accretion disk. Others were captured from distant regions. Some were born through giant impacts. In collision models, debris is ejected into orbit, forming a ring that slowly gathers into a satellite. Earth's moon is believed to have formed in this way. A massive impact between the young Earth and a Mars-sized body may have created our companion. The moons of gas giants are especially fascinating. Some are icy, some rocky, some mixed. Some hide oceans beneath their surfaces. Others host active volcanoes. Some possess thick atmospheres. Others have almost none. Tidal forces within these systems generate internal heat. This heat can power volcanic activity and maintain liquid water below ice shells. Even far from sunlight, these moons may sustain chemistry for billions of years. One of the most important structures is the asteroid belt, located between Mars and Jupiter. It contains millions of objects, yet its total mass is only a small fraction of Earth's moon. One idea suggests it is the remains of a planet that never fully formed. Another proposes that Jupiter's gravity prevented accretion. Gravitational resonances create empty regions known as Kirkwood gaps. Asteroids fall into different types: rocky silicate bodies, metal-rich objects containing iron and nickel, icy bodies rich in frozen volatiles. This diversity reveals formation across a wide range of temperatures. Some asteroids migrated from their birthplaces. Others were reshaped by collisions. Many rotate irregularly. Some experience the Yarkovsky effect, a tiny thrust caused by thermal radiation, which slowly alters their orbits over millions of years. Beyond Neptune lies the Kuiper Belt, a vast realm of icy remnants. Here reside dwarf planets such as Pluto. Their orbits are often elongated and tilted. Many objects exist in resonance with Neptune. Even farther may lie the Oort cloud, a distant spherical reservoir of icy bodies. It is believed to be the source of long-period comets. Comets are frozen archives. When they approach a star, their ices sublimate. Gas and dust form a glowing coma and long tails. One tail is dusty, another is ionized. Solar wind shapes the ion tail. Sunlight pressure shapes the dust tail. Comet nuclei contain organic molecules, frozen gases, and primordial grains. They reveal the chemistry of the early solar nebula. Some models propose asteroids with internal cavities. Others may be rubble piles, loosely bound collections of fragments. These bodies can tumble, change rotation direction, and evolve slowly over immense time scales. Even small bodies can have moons, binary asteroids, triple systems. These configurations provide clues about mass distribution and density. Close encounters with planets can alter small body orbits. Some are sent inward. Some collide with planets. Craters on the Moon and Mars testify to intense bombardment in early history. This era may have shaped planetary surfaces and possibly influenced the emergence of life. Icy bodies may have delivered water to inner planets. Comets and icy asteroids could have supplied Earth's oceans. There are even hypotheses about a large unseen planet far beyond Neptune, sometimes called Planet 9. Its existence remains uncertain. If confirmed, it would reshape our understanding of the outer solar system. Small bodies also interact with gas, dust, radiation, and magnetic fields. They drift, they collide, they evolve, quietly, patiently, holding within them the ancient memory of how worlds begin. In the earliest epochs of a protoplanetary disk, gas can slow the motion of solid objects, causing them to drift inward toward the star. This process may explain why many rocky worlds form close to their suns. If an object becomes large enough, it can retain a thin envelope of gas, making it resemble a miniature giant. Even tiny bodies feel subtle forces. When one side of an object is warmed by starlight, thermal radiation produces a faint thrust. Over immense spans of time, this gentle push can slowly reshape an orbit. These phenomena are known as thermodynamic effects. They remind us that even the weakest forces, acting patiently, can sculpt the architecture of planetary systems. It seems paradoxical that the nearly empty space between stars plays such a powerful role. In a single cubic centimeter of interstellar space, there may be only a few atoms. Yet this sparse medium influences the motion of light, the birth of stars, the cooling of galactic disks, and the distribution of energy across scales as large as galaxies themselves. Many of these processes cannot be recreated in laboratories because they unfold over distances and times far beyond human reach. Cosmic dust is composed of particles ranging from fractions of a micrometer to several tens of micrometers. These grains are forged in the atmospheres of red giants, in the debris of supernova, and within the disks of young stars. They may contain graphite, silicates, metal oxides, and icy coatings. Dust plays a crucial role in cooling clouds. By emitting infrared radiation, dust allows clouds to lose energy, contract, and eventually collapse. In this quiet way, dust becomes a midwife of stars. The interstellar medium exists in several phases. A cold phase, rich in molecular hydrogen, where stars are born. A warm phase, containing atomic and ionized gas. And a hot phase, heated by supernova explosions and energetic stellar winds. These phases can coexist within the same region. Hot gas can carve cavities, compress neighboring clouds, or trigger new waves of star formation. Some hypotheses suggest that much of the interstellar medium may exist in hidden forms. Cold molecular gas that emits little radiation. Large dust aggregates that absorb light but glow faintly. Complex molecular structures capable of surviving harsh cosmic environments. The interstellar medium is rich in organic molecules. Spectral observations reveal hydrocarbons, long carbon chains, and even molecules resembling amino acids. These compounds form under ultraviolet radiation, shock waves, and chemical rearrangement. Their presence raises profound questions. How common are organic molecules in the universe? Are the chemical pathways toward complexity universal? Between galaxies, density becomes even lower. Yet observations show vast reservoirs of extremely hot gas stretching across intergalactic space. This gas is shaped by galaxy interactions, energetic outflows from galactic nuclei, and cosmic mergers. Recent evidence suggests that a large fraction of ordinary matter may reside in these tenuous structures. They influence the motion of galaxies and the evolution of clusters. Some models describe the intergalactic medium as a network of filaments and nodes, an extension of the cosmic web. These filaments connect galaxies, channeling matter inward. Such flows can replenish gas and sustain star formation. When supply diminishes, galaxies slowly fade. There is also speculation that dark matter may weakly interact with gas in these regions. If so, subtle temperature patterns might reveal its influence. These ideas remain under investigation. Inside interstellar clouds, turbulence is everywhere. Chaotic motions create regions of enhanced density. In some places, turbulence helps stars form. In others, it tears structures apart. Its role is both creative and destructive. Supernova explosions may continually inject energy, sustaining this turbulence. Shock waves travel through space, They arise from stellar explosions, colliding clouds, and fast-moving objects. Shocks compress gas, raising density. New stars can emerge along these compressed fronts. This can lead to chain reactions, forming entire clusters. Some matter may remain hidden in extremely cold clouds that emit almost no detectable radiation. Finding these reservoirs is a major goal of modern astronomy. Interstellar dust absorbs and scatters light, producing interstellar extinction. Distant objects appear dimmer and redder. Yet this absorption allows scientists to map dust and infer cloud structure. Ionized gas interacts with magnetic fields. Magnetic waves ripple through space. These fields can resist collapse or guide the flow of matter. Magnetism may have played a major role in the early formation of galaxies. How cosmic magnetic fields originated remains an open question. One possibility is amplification through rotation and turbulence. Radiation also shapes clouds. High-energy photons break molecules apart, creating ionized regions. These photodissociation regions often surround young, luminous stars. They are dynamic boundaries where chemistry, radiation, and gravity meet. These regions play a crucial role in the birth of new planetary systems, because the conditions within them determine the composition of dust and gas. Some models suggest the existence of hidden forms of chemistry that emerge at extremely low temperatures and under intense radiation. On the surfaces of tiny dust grains, subtle reactions may occur, slowly assembling complex molecules. This expands our understanding of what chemistry is possible in space. It transforms the seemingly empty cosmos, filled with faint vibrations of particles, into a vast laboratory where energies arise far beyond anything human technology can produce. This leads us to a fundamental question. What is the true nature of cosmic radiation? Streams of particles travel through space, carrying messages from distant and violent events. By studying them, we learn how matter behaves under relativistic speeds, powerful magnetic fields, and extreme temperatures. Cosmic radiation consists mainly of charged particles, protons, helium nuclei, electrons, heavier atomic nuclei. Some of these particles possess energies greater than those produced by Earth's largest accelerators. In rare cases, a single particle carries energy comparable to the kinetic energy of a tennis ball in motion, compressed into one microscopic entity. This alone reveals how extraordinary cosmic accelerators truly are. The sources of these particles are diverse. Supernova explosions, active galactic nuclei, powerful magnetic fields of neutron stars, jets near black holes. One widely accepted mechanism is shock acceleration. When a supernova explodes, its shock wave plows through interstellar space. Particles cross the shock front again and again. Each crossing adds a small amount of energy. Over time, these small gains accumulate, producing highly energetic particles. This is known as first-order Fermi acceleration. It explains much of the medium-energy cosmic radiation. Yet some particles reach energies so immense that standard models struggle to explain them. These are called ultra-high energy cosmic rays. They may originate near supermassive black holes, where gravity and magnetic fields create extreme environments. Another idea suggests that interactions with the cosmic microwave background limit how far such particles can travel, imposing an upper energy boundary. Interstellar and intergalactic space is threaded with magnetic fields. Even weak fields can bend particle trajectories over vast distances. Because of this, tracing cosmic rays back to their sources is extremely difficult. When these particles strike Earth's atmosphere, they collide with air molecules and generate cascades of secondary particles. By analyzing these showers, scientists infer properties of the original cosmic rays. Beyond particles, electromagnetic radiation is equally important. Gamma rays, X-rays, ultraviolet light, visible light, infrared radiation, radio waves. Each band reveals different processes. Gamma rays arise near black holes, in strong magnetic fields, and during violent cosmic explosions. Gamma ray bursts are among the most powerful events known. Short bursts last at a couple of seconds and may result from merging neutron stars. Long bursts can last tens of seconds and are linked to the collapse of massive stars, forming black holes. These flashes are so intense, they can be observed across billions of light years. X-rays originate in hot gas, accretion disks around black holes, and neutron stars. Temperatures in these regions reach millions of degrees. Atoms become ionized. Electrons collide with nuclei. X-ray photons are released. Through this radiation, we glimpse environments of extraordinary density and gravity. Infrared radiation traces cold matter. Dust and gas glow softly as they release heat. Infrared telescopes peer into dark clouds, revealing protostars and planetary nurseries hidden from visible light. Radio waves often come from charged particles spiraling around magnetic field lines. This is called synchrotron radiation. It illuminates supernova remnants, galactic centers, and colossal jets. These jets can stretch hundreds of thousands of light years. Their radio glow maps magnetic structures and particle densities. Some theories propose that dark matter interactions might produce radiation. If dark matter particles annihilate or decay, they could emit gamma rays or other signals. These ideas remain unconfirmed, but they guide ongoing searches. Cosmic radiation also shapes star formation. High-energy particles ionize gas. Ionization influences cooling and chemical pathways. In cold molecular clouds, cosmic rays may help create complex molecules. In this way, they participate in the earliest chemistry of future worlds. There are even hypotheses that cosmic radiation may subtly affect planetary climates by influencing cloud formation. This remains a topic of debate. The relationship is intricate. Magnetic fields play a central role in particle acceleration. They grow stronger through motion and turbulence. They trap charged particles, holding them for long periods. Some regions behave like natural particle accelerators, jets from active galaxies, shock fronts, boundaries between different gas phases. Here, particles reach relativistic speeds. Special attention is given to neutrinos. They have extremely small mass. They interact very weakly with matter. They pass through planets, stars, and entire galaxies almost unhindered. Because of this, neutrinos carry pristine information from the deepest cosmic engines. They are silent messengers from the heart of the universe. Cosmic neutrinos carry information about processes unfolding deep inside stars and in the immediate surroundings of black holes. They allow us to glimpse what happens in regions that are otherwise completely inaccessible. And this leads to an even deeper question. What makes matter attract matter? Why does this interaction shape everything we see, from the motion of tiny particles to the majestic dance of galaxies? This question lies at the heart of physics. Yet the true nature of gravity remains only partially understood. On everyday scales, gravity behaves in ways we can predict. But on the largest cosmic scales, subtle effects emerge that challenge our understanding. Gravity governs dynamics. It forms orbits, creates density waves, guides the evolution of stars, galaxies, and clusters. Our modern description of gravity comes from Einstein's general theory of relativity. In this framework, gravity is not a force in the traditional sense. It is the curvature of spacetime, caused by mass and energy. Objects move along paths dictated by geometry itself. This elegant idea explains the bending of light, the precession of planetary orbits, gravitational lensing, stellar collapse, the existence of black holes. Yet an important question remains. Is this theory fundamental, or only an approximation of a deeper underlying reality? One of the most powerful tools for studying mass in the universe is gravitational lensing. light passing near a massive object is deflected. This allows us to see galaxies far beyond what would normally be visible. Lensing reveals something extraordinary. Much of the universe's mass is invisible. This unseen component is called dark matter. Maps created from lensing data show vast structures of hidden mass threaded throughout space. In many galaxy clusters, the total gravitational mass far exceeds what we observe in stars and gas. This tells us that visible matter alone cannot explain cosmic dynamics. Another revolutionary window into gravity came with the discovery of gravitational waves. These are ripples in spacetime itself, produced when massive objects accelerate. They were first directly detected in the 21st century. Gravitational waves carry information about events impossible to observe otherwise. Black hole mergers, neutron-star collisions, extreme cosmic explosions. They allow us to test gravity in its most intense form. Some physicists suspect that gravity may have a quantum nature. One hypothetical particle, the graviton, would mediate gravitational interactions. However, detecting such a particle is extraordinarily difficult because gravity is so weak. Developing a quantum theory of gravity that unites relativity and quantum mechanics remains one of the greatest challenges in science. Another deep puzzle involves vacuum energy. Quantum theories predict that empty space contains enormous energy, but observations of cosmic acceleration suggest a much smaller value. This mismatch is one of the largest discrepancies in all of physics. Some theories propose hidden cancellation mechanisms. Others suggest extra dimensions where energy may be distributed differently. On very large scales, gravity itself might behave differently. Some models modify gravity to explain cosmic acceleration without invoking dark energy. If gravity weakens over great distances, the expansion of space could speed up naturally. These ideas remain under active investigation. Despite these mysteries, Einstein's equations still describe countless phenomena with remarkable accuracy. Planetary orbits, stellar motion, black hole dynamics, gravitational collapse, yet anomalies persist. For example, stars at the edges of galaxies orbit much faster than expected. This observation supports either the existence of dark matter or a modification of gravitational laws. Dark matter does not emit, absorb, or reflect light. It interacts primarily through gravity. It may consist of weakly interacting particles, exotic atoms, or unknown composite structures. Although not directly detected, its gravitational fingerprints appear throughout the cosmos. Dark energy drives the accelerated expansion of the universe. Its nature is unknown. It may be a property of space itself, or a dynamic field that changes over time. Some theories suggest that what we call dark energy is actually a sign that gravity behaves differently on cosmic scales. Gravity shaped the universe from the beginning. Tiny density fluctuations grew under gravitational attraction. Clouds formed. Galaxies assembled. Clusters and superclusters emerged. Gravity determined where structures formed, how fast they grew, and how they are arranged today. Within galaxies, gravity controls the motion of stars. Observations show that galactic halos contain far more mass than visible disks. This hidden mass stabilizes rotation. It keeps spiral arms coherent. It prevents galaxies from flying apart. Inside galaxy clusters, gravity becomes even more dominant. Clusters contain enormous amounts of hot gas, emitting X-rays. Only strong gravitational binding can keep this gas confined. Once again, the required mass exceeds what we see. Gravitational segregation occurs in dense systems. Heavier objects gradually sink toward the center. Lighter ones drift outward. This reshapes star clusters over time. Central regions may accumulate neutron stars, white dwarfs, and black holes. Galaxies also interact gravitationally. They merge, stretch, distort. These encounters create tidal bridges, long tails. ring-like structures. Such features reveal the immense complexity of cosmic motion. Some speculative theories propose that gravity may be linked to thermodynamics. In these models, gravity emerges from entropy and information. If true, gravity would be a collective phenomenon, not a fundamental force. This idea could explain why gravity is universal and shapes the cosmos on every scale. On small scales, mathematical models allow us to describe the motion of objects with remarkable precision. The paths of planets, the behavior of stars, and even the interactions of tiny particles can be predicted with extraordinary accuracy. But when we move to scales comparable to the size of the entire observable universe, new phenomena appear that require a much deeper and more subtle approach. The distribution of galaxies forms a structure that resembles an immense network, often called the cosmic web. Within this web, there are long filaments, dense nodes, and vast empty regions known as voids. Superclusters unite thousands of galaxies. These enormous structures are distributed unevenly, even though, on average, the universe tends toward large-scale uniformity. The largest structures in the universe form under the combined influence of gravity and primordial density fluctuations. These fluctuations arose in the very early universe and were gradually amplified by gravity, creating regions of higher and lower density. Galaxies and clusters grow along filaments. Between these filaments lie enormous voids. Although voids appear empty, they can still contain extremely diffuse gas and dark matter. In some observations, scientists detect cold spots regions where the temperature of the cosmic microwave background is slightly lower. These cold spots may correspond to especially large voids. All of these structures continue to be studied in order to understand how they influence the long-term evolution of the cosmos. The cosmic web forms the large-scale framework of the universe. Within this framework, galaxies move under the influence of gravitational forces. Their motion is often directed toward dense nodes. In some regions, galaxies slowly flow toward massive superclusters. These gigantic structures possess enough mass to affect the dynamics of neighboring regions of space. Superclusters can have complex shapes and may contain several massive galaxy concentrations. They are distributed unevenly across space. Some regions of the universe are rich with superclusters, while others appear relatively empty. One important area of research is determining the overall shape of the universe. Cosmic geometry may be flat, open, or closed. A flat universe follows the rules of Euclidean geometry. Observations of the cosmic microwave background suggest that the observable universe is very close to flat. However, small deviations are still possible, which could indicate slight curvature. An open universe would have negative curvature. A closed universe would have positive curvature. In a closed model, space may be finite in volume, yet have no boundaries. In an open model, space is infinite and continues to expand forever. The expansion of the universe is one of its most fundamental properties. It was discovered through the study of light from distant galaxies. The farther a galaxy is, the faster it appears to be moving away. This relationship is known as Hubble's law. Modern cosmology shows that the rate of expansion has changed over time. In the early universe, expansion was extremely rapid. Later, gravity slowed it down. Eventually, expansion began to accelerate. This acceleration is attributed to dark energy. Research indicates that accelerated expansion is a central feature of the modern universe. Many hypotheses attempt to explain the nature of dark energy. One model suggests that dark energy is a property of the vacuum itself. Another proposes that it is a dynamic field whose strength changes over time. Some models connect dark energy to the geometry of space. If space possesses an internal structure, changes in that structure could drive cosmic acceleration. These ideas are still actively debated. Understanding dark energy is one of the greatest challenges in contemporary cosmology. An especially fascinating question concerns the fate of the universe. If acceleration continues, the universe will expand forever. Galaxies will drift farther apart, and interactions between them will become increasingly rare. In some models, acceleration may intensify. Distances would then grow faster and faster, eventually tearing cosmic structures apart. Other models suggest that acceleration could slow down, stop, or even reverse. In such cases, the universe might begin to contract. These outcomes depend on the balance between matter, and dark energy. There are also hypotheses that the universe may be cyclic. In cyclic models, the cosmos expands, then contracts, and then expands again. These cycles could repeat endlessly. Such models often treat gravity and quantum processes as mechanisms that regulate expansion and contraction. So far, observations provide no direct evidence for cosmic cycles, and further data is needed. A special role is played by the cosmic microwave background radiation. This ancient light comes from the early universe. By studying it, scientists learn about the density, temperature, and composition of the cosmos shortly after the hot initial phase. Tiny temperature variations in this radiation reflect the primordial fluctuations that later formed galaxies and large-scale structures. The temperature is nearly the same in all directions, with only very small variations. These variations contain a wealth of cosmological information. Some models suggest that the cosmic microwave background may contain subtle traces of enormous structures beyond the observable universe. If regions exist outside our observational horizon, their influence might appear on the largest scales. This idea remains speculative, but it continues to attract scientific interest. Voids play a crucial role in cosmic structure. They are regions with extremely low matter density. Voids can span hundreds of millions of light years. They form as matter gradually flows into denser regions. Even so, voids may still contain gas and dark matter. Studying voids helps scientists understand how matter is distributed throughout space. Voids are a fundamental component of the cosmic web. There are hypotheses about the existence of large cold flows. These flows may indicate motion of structures beyond the observable universe. Some observations reveal weak preferred directions in space. These signals are still under interpretation. They may result from statistical fluctuations, or they could hint at enormous unseen structures. The multiverse is another hypothesis in modern cosmology. According to this idea, our universe may be only one among many. Different universes could have different physical laws. They may be connected or completely independent. The multiverse concept arose partly to explain why physical constants appear finely tuned. If many universes exist, some would naturally possess conditions suitable for stable structures and life. Some models propose the existence of bubble universes. Each bubble may represent a separate universe. These bubbles could form through processes in a quantum vacuum. If such processes occur continuously, new regions of space would constantly emerge. This idea is known as eternal inflation. It suggests that cosmic creation never truly ends. Other hypotheses explore the possibility of extra dimensions. If space has additional dimensions beyond the familiar three, they could influence particle behavior and gravity. In certain theories, particles may move through these hidden dimensions, producing new physical effects. So far, no direct evidence for extra dimensions has been found. The structure of the universe may be far more complex than simple models suggest. Some studies indicate the possibility of a global asymmetry. Weak deviations from perfect symmetry have been detected in the cosmic microwave background. These anomalies may be remnants of processes from the very early universe. They continue to be carefully investigated. The more we learn about the cosmos, the more we realize how vast, subtle, and profoundly mysterious it truly is. And each discovery opens the door to even deeper questions about existence itself. And so, as we slowly drift through these immense cosmic ideas, we begin to understand that the universe is not only a place of matter and energy, but also a vast ocean of mystery, silence, and endless possibility. Every galaxy, every filament of the cosmic web, every invisible particle moving through space whispers a quiet story about existence itself. We are made from the same atoms that were once forged inside ancient stars. The same forces that shape galaxies also flow through us. And perhaps, in this boundless darkness, the greatest discovery is not only how the universe works, but the quiet realization that we are part of it. Floating, breathing, observing, wondering. Let these thoughts slowly fade into the silence of space, where time moves gently and curiosity never truly sleeps. Rest now and allow your mind to travel among the stars.